So my name's Sean. This is my 12th time, I think, at these conferences. Sorry. Better? So I'll be looking at the advances that we've made to the LIBFABRIC APIs. And a lot of these are gathered up over the course of the past 2 to 3 years. I apologize now for the lack of plot in my slides. So these features should show up in the next release. So this is going to be targeting the 1.5 release of LIBFABRIC. All of LIBFABRIC and all of the OpenFabrics interfaces in the working group were primarily driven by the applications. So the interfaces are driven by the applications, the semantics, the requirements, all come from the applications. In some cases, there were features that were requested by applications that we simply deferred until we had time to analyze them more and bring them in. There are also new applications that we're looking at, so new opportunities to expand LIBFABRIC into other markets, such as cloud, HPC, and some of those are driving the features. We've got feedback from different users, both developers, but also end users. What do they want to see change? And that's helped provide some input. And then also feedback from the providers. So some of the providers, they would look at certain features, and it was hard for different providers to implement some of the features, at least in a performant way. So we're using all these to kind of build up. Over the past 2 to 3 years, what we did is we collected any feature that we thought would change the API in some way. We gathered those all up, and we're going to have one release that kind of addresses all those at once. And we'll probably do the same thing. We'll continue to gather features that we think may change the API. Not all of them do, but some, if we think it will, try to put those in another 2 or 3 years in those cases. So the 1.5 release, not going to break any applications. Your applications continue to work. There's just going to be new features that are added. Obviously, the applications will need to move to the 1.5 release to take advantage of them. So from the user side, one of the requests we got was, can we have a developer guide? Right? Again, this isn't really API, but so if you're wondering what I do with my weekends, this is it. So I have a developer guide. So we have this out on GitHub. It's just in a markdown language. I don't have it formatted. But you can go out to GitHub. You can go through the developer guide. The intent here is it provides a fairly broad coverage of what OpenFabrics Interfaces is trying to do, what the requirements are, what the design is, and look at the architecture. So it does assume a fairly minimal background. It starts out, I talk about sockets, talk about client-server, how to establish connections with sockets, look at the socket API, how does select and poll work, how we look at non-blocking sockets. And the sockets is there really to kind of as a background, but also for reference later, because it's more widely known than, say, LIBFABRIC or LIBIB-verbs or other higher performance interfaces. So it gives kind of a reference back to a developer as to, how does this compare to sockets? Then we looked at what, talks about what are the requirements from high performance computing. So what does high performance computing want? And how does that, the sockets API, for example, meet those needs or not meet those needs? We talk about stuff like memory copies. Like socket API results in memory copies. If we look at asynchronous operations, what does it mean if I say, I want to submit a work request and then come back later and check to see when it's done? And how does that impact the API? Moves on, it talks about API trade-offs. Some of this stuff I've actually talked about at this conference a couple years ago. As we design these APIs, how does that affect what the application sees and how does that affect performance? And then from there we kind of break down what are the communication primitives that all this leads to. How does this result in command queues? Where does the buffering reside? We talk about ordering. So as you send messages across the network, what order do they arrive in? How does that impact, for example, switching? Am I able to take advantage of multiple paths through the network? And everything up to this point is fairly generic. So I don't really talk about OFI for maybe 40 or 50% of the guide here. So the intent is that anybody who's new to either RDMA, maybe verbs, LIBFABRIC, asynchronous operations, they could actually maybe use the beginning part of this to understand a bit better about how these high-performance APIs are designed. So there's a link there. It then talks about the actual architecture, the design, some of the interfaces, and then the trade-offs that would be made as an application selects different capabilities or modes. What does the impact of that, what could the impact be on a provider and the implementation? So those are in conjunction with the man pages. It is separate. So for the architecture, I'm not going to talk in detail about the architecture. Just wanted to kind of refresh for people not familiar. In OFI terms, we have what we call capabilities and modes. The capabilities are the set of features that the application wants. For example, application may want, I want to send and receive messages. I want to do RDMA read and writes. Maybe they need tag matching. So the capabilities are what the application features push down. The modes are really driven by the providers. So the modes say, well, if you want capability X, say RDMA, then it requires certain functionality out of the application. For example, there may be a mode that indicates memory registration. So if you want to do RDMA, I need you to register memory. So the mode bits are kind of pushed up from the application, or sorry, from the provider up to the application on how these need to be used. And we have changes here to both capabilities and the mode bits that I'll talk about. So one of the new capabilities, authorization keys. So this was added in to support kind of job isolation. So if you're on a large cluster and you want to have 2 jobs, 3 jobs, 10 jobs talking, but you don't want them to crosstalk, you don't want one to access the other one's memory, we do allow providers to support authorization keys. After talking with the different providers, for example, Omnipath, Cray, the GNI, the Blue Gene, they have some way of having some of this sort of protection and these job keys built into their hardware and to their providers. And we also spoke to the application saying, what do the applications want out of these? Because we had a lot of different options to choose from here. And the one we settled on was, for every endpoint, we wanted to allow a key. So if provider supports it, the endpoint's associated with some sort of key. In order to talk with any peer, you have to have the same keys. So if you have different keys, 2 endpoints can't talk. The second thing we wanted to add was when you register memory or expose memory to the network, for example, RDMA target, either a read or a write, we wanted to be able to associate that with the key as well. So if you have an application that's talking, right, the application has 2 different sets of peers that you're dealing with. Maybe one's a set of compute side, the other job part is storage to save the data. And they wanted to keep that traffic separate. We wanted to be able to add a key to the memory regions. So when the application registers memory, they specify a key, and only endpoints with matching keys can access that region. So the memory region, the endpoints all have to align for it to work. Multicast. So this was a feature that was requested up front when we started doing our requirements. So we've defined how to integrate multicast into this. The biggest challenge we had and what took us so long, which you won't be able to tell from the solution here, was when an application, so they want to join a multicast group. So they join a multicast group, how do they get an address for that group? All right, so we added a new call, we extend the API, they call join, they get an address back, and now we had an issue where, let's say you do a send message to a provider. How does the provider know that the address you're giving it is a multicast address versus a unicast address? Well, one way is, provider has to reserve some sort of bit. So in their address, they say, okay, bit 0 indicates whether I'm unicast or multicast. So we actually push this problem up to the application. The application knows if they're sending to a unicast address or a multicast address. So to use multicast, the application simply adds a multicast flag to the operation, and now the provider knows that this is a multicast send, for example. From an API perspective, we've only defined multicast for datagram endpoints, and only for message send receive. So there's nothing that prevents us from expanding this. For example, if we had a reliable multicast, we could support that through the API. We just don't define that because we don't know if there's anybody who actually implements it at this point. Beyond HPC, so somebody asked me in the hall yesterday, the day before, about what about RSockets? Are we doing anything with that? And the answer is yes. So when we started looking at RSockets, I looked at the implementation. So, well, let me take RSockets implementation and can I import it over LibFabric? And then we looked at other APIs that are used in maybe cloud enterprise space. And one example here is 0MQ. If you're not familiar with 0MQ, it's an abstraction on top of sockets. And the 0MQ API really assumes that the underlying implementation is sockets. So when we looked at, if I take the RSocket implementation, for example, and I move that directly over LibFabric, the RSocket implementation is designed around verbs. Right? It works well if you're a verbs device. But if you're not a verbs device, it actually can cause a mismatch. And instead of having one data copy to do sends and receives, you end up with two. So our solution was to actually create a new endpoint type. So LibFabric currently has 3 endpoint types: unreliable datagram, reliable datagram, and just reliable connected. So we have new endpoint types: sock stream and sock datagram. And the semantics of these endpoint types are they operate synchronously. So the application is always in charge of the buffer. So the application calls send on a sock stream or sock datagram. When that send call returns, the application gets the buffer. How the provider wants to deal with that buffer and how they want to transfer the data is really provider specific now. So what this ends up doing is it takes, for example, in the RSockets implementation, the data transfer portion of that implementation moves down to the provider. So there's no loss in performance there, at least, for example, RSockets over verbs. You still have that same capability. But from an API perspective for LibFabric, since we're dealing with synchronous operations, these new endpoint types don't have completion queues. Right? You call send returns, the buffer's there. So there is no reason to report a completion. The other thing we have is these applications are relying on calls like select and poll. So in order to block on select or poll, we require that these new endpoint types have some sort of file descriptor associated with them that can be exposed to the application that the application can then access. Now, we're not moving a full socket implementation under these APIs, for example. The datagram socket still uses the address vectors of LibFabric. The stream socket still has to bind to event queues. It still has the CM API, so it still deals with the asynchronous CM communication or connection management. But now the data transfers can be optimized based on what the provider actually can do and do well. Atomic operations, again, adding more atomics. So most of the time we look at atomics, most people can think of atomics and RDMA as together. So you register a buffer for RDMA capabilities, you can do atomics on it as well. So when we looked at the API, and we looked at, like, for example, what MPI was wanting, when an application's sending an atomic operation, atomic increment across the fabric, they specify really two pieces of information. One's a key, so the registration key associated with the region, and the second's the address. Well, when you look at the key and the address, it's really the key that determines the remote buffer. The address is really the offset into that buffer. So I said, well, if you're using if it's the key that's determining the buffer, conceptually a key and a message tag are the same. So can we support atomics to tagged messages? So through the API, we added basically a single operation flag. If the application specifies tag, then the key they're giving us is really interpreted as a message tag, and the atomic operation goes to the remote tagged message queue versus a remote RMA buffer. So deferred work queues, I'm going to skip details here for time, but this is kind of a first step in trying to work through how do we expose an implementation agnostic way of basic collective offload support. So that one's experimental, so we're free to change it, but that's our first step to try to get there. So a little bit about some of the users, what applications we're looking at. In terms of providers, this is one of these mode bits that we want the providers to be able to have access to. So 2 ways to optimize completions. One, when an application asks a provider, say I want to allocate a completion queue, from a provider's viewpoint, they don't know how that completion queue will be used. So they have to assume the worst case. They have to assume that this completion queue may be used to complete RDMA operations, message, tag message operations, and they have to set up the completion queue as if the worst case is going to happen. So the restricted completion mode bit basically allows the application to indicate to the provider that all of its endpoints on this completion queue will be the same. So if he creates an endpoint that has only RDMA capabilities and binds it to a completion queue, then that tells the provider that it only needs to deal with RDMA completions. It never has to deal with tag matching completions. And what this allows is it allows the provider to eliminate some post-processing. Example, if you're using verbs provider, verbs does not have tag matching naturally, so that has to be emulated in software. If we're implementing if I'm allocating a completion queue and an endpoint, I'm only doing RDMA, and I say restricted completion, now the verbs provider knows that, hey, I don't have to deal with tag matching. This is simply an RDMA completion. I can just pass that completion straight through from the underlying hardware up to the application. Completion data, a couple other changes. One's in semantics. So LIBFABRIC's optimized around reporting successful completions. So when the application says read a CQ, it gets back a successful completion. If the next operation in the completion queue failed, right, so something failed, they did a send, it timed out, and there's a failure, then when the application tries to read the completion queue, they actually get an error. And that error indicates to them, the next completion, you must call this read error function instead. And what that allows us to report additional error information to the application. Right, so your next operation failed, call read error on the CQ. That gives you more data. The problem that we had is the semantics for that didn't work well with multi-threaded applications. So if you have an application that has 3 or 4 threads all reading the exact same completion queue, we simply changed the error handling semantics to make it a little bit friendlier for those applications. The source error capability. So imagine you have a server application running, you're on a network, you have 1,000 nodes, and some client actually sends you a message. As a server, what you want to know is, have I ever spoken to that client before, and do I know how to respond to that client? So what the source error capability ends up adding is, it tells the provider that if you get a message from a client, I want you to first verify that that message from the source is actually in my local address vector. Tell me if I know who that sender is. If I don't know who the sender is, still give me the message, but then give me the addressing information about that sender. And then at that point, the server application can now, okay, I got the message, I have their address, I can either choose to drop the message, I can take their address information, add them to my local address vector, and then send the reply. So it's simply trying to make it life a little bit easier on the application to not have to track which servers, which clients have I spoken to already, and not have to do their own independent connection establishment over an unconnected channel. Feature grab bag. So up to this point, we really haven't had to deal with what version we're dealing with. So when I mentioned that this is, we're going to actually change the ABI. So the ABI goes from 1.0 to 1.1. There's just these few attributes that are driving that change. So the ABI change is the result of having basically 3 attributes added to some structures. And one of these is the API version. It turns out that some applications link in 2 different libraries, right? So they may link in MPI and they link in SHMEM. Well, the MPI might be coded for the 1.5 release. SHMEM might be coded still for 1.0. By adding the API version, what we're trying to do here is we want to allow the provider to determine I'm being used by 2 different libraries, and they want different versions and different semantics. So we simply added an API version to our Fabric attributes so that when the application opens the Fabric, the provider can check which version that library is actually trying to use. We added string-based addressing. So what all this does is we had, I think it was like a job manager or process manager was wanting to be able to collect addresses as strings, distribute it to all the processes, and then have them take those strings and convert it back. So LIBFABRIC tries hard to make the addressing, basically the application shouldn't care what the addressing is. So if I'm running on IP network, you're going to have a sock adder. If I'm running on Omnipath network, you're going to have some other format. If I'm running on InfiniBand, I could have maybe a sock adder IN, maybe a sock adder IB. It tries to make it so the application can just exchange the addressing data without caring what the actual format is. The string format's the exact same way. It's just saying all providers need a way to convert their native addressing into a well-known string format that can then be interpreted by somebody on the remote side. Communication scope. So it turns out that we have providers that cannot communicate with both loopback and across the network. So the communication scope, we have local and remote bits set. So as a provider, you can look, sorry, as an application, you can look at the provider and say, does this provider support only local communication? For example, maybe it's shared memory. Or does this only support remote communication? US NIC, for example, has this issue where they only can talk to remote nodes. They can't talk and look back. We're hoping that this near-far is going to be sufficient for communication scope, and that we don't need to expand this to anything beyond local and remote. But we have that option if we need to. If we ever need to look at the communication, for example, only works with an accelerator, we at least know of a way that we can try to expand that. Provider updates, kind of spoke about this a little bit last year. So the 1.5 release should start including the utility providers. The only change we've made to the utility providers is that they're kind of what we would call a shadow provider. So as an application, if you're used to saying, I want provider US NIC, but you want features, say reliable datagram, you automatically pick up the utility provider over US NIC. So from an application, the basic utility providers are as transparent as we can make them. You can still deal directly with just the lower level hardware provider and don't have to worry about the names of these utility providers. Decoding ring for utility providers, if you're interested, so they all have this OFI prefix in the name. So if you wanted to create your own utility provider for whatever reason, you just need to add the OFI prefix to it. And it's usually going to have some endpoint type laid over some other endpoint type, such as reliable datagram layered over unreliable datagram. We have 2 new providers. I'll actually put one on the slide. So there's an MXM provider that was deprecated. We have a new Mellanox provider that was added in that'll be in the 1.5 release. And there's also a network direct provider that's going to be merged in shortly. Memory registration. So this was painful. So in our initial discussions of what the applications want for memory registration, how do they want to handle, we came up with really 2 solutions. So and I made this an enum actually. So I tried to limit it what the applications had to do. So at one end you have what the applications wanted, which we called Mr. Scalable. Mr. Scalable, register all of the physical memory. You don't have to, application can pick the key that's used, so you don't have to exchange keys. And then we had the reality of, well, that's nice what applications want, but the hardware doesn't do it. So then we created Mr. Basic, and Mr. Basic is really there to align with traditional RDMA fabrics. So this is what Rocky, InfiniBand, iWarp end up supporting. And it turns out that there's some fairly important HPC systems that are, I'm going to call them Mr. Neither. They're neither basic or scalable, and they have to emulate both. Right? They can't move the scalable because of some features missing, but it's actually hard for them to drop back to basic. So what we did, and this is where the community, I disagree with the community on this, but the community won. So what we did with the mode bits is we took the enum that had just the 2 choices, and we broke that into integer flags. So from the integer flags, basic, so what used to be known as basic, we split that up. What did basic actually represent? It represented really 3 different things. First, as you had at the bottom right there, the provider selects the memory key. So who selects the key? If that node bit is set, the provider tells you what the key is. Do you have to have physical pages backing your memory when you register? Right? So if you have to have allocated memory on the registration call, the memr allocated bit will be set. And then how do you identify the offset into a region? We mentioned kind of the key is really identifying the region. How do you find the offset? Are you using the virtual address as a starting point, or are you using a 0-based address? So the virtual address would be based on the virtual address of the registration. Otherwise, if that bit's not set, it's assuming a 0-based offset. And to add to that, typically these basic mode bits are paired with what we call local. In local, it says that you need to register all data buffers that are used with transfers. Not just, so we require registration on anything that is accessed through RDMA or atomic. So anything for security reasons, we require registration. For local sends, local receives, or source RMA buffers, it's not required unless the local bit is set. Raw memory regions, so now we've started expanding, not just basic and scalable. So raw is used to support providers that need more than 64-bit keys, or if they require some sort of setup on the target side. So with the raw registration, with that bit set, on the target side, they have to register. They get the raw attributes. They hand that over to the initiator side, and the initiator side has to map those attributes in. This was a feedback based on an implementation done over the A3 Cube hardware. I think this is the last one. There's a couple other mode bits we ended up adding to support the various providers. So MMU notify was added. So this allows an application to register memory where they do not have physical pages backing the memory. The provider can set up the registration, and if any of those memory pages change, the user is responsible for notifying the provider that those changes have occurred. And then the provider actually brings in the mapping. So this is for NICs where they can register all of virtual memory, for example, but they have to be told, they're not hooked into the memory management unit. They actually have to be told that, okay, all the memory that I'm going to have access is now there. Update your page table entries. So we're really trying to balance, what do the users want? What works well for the providers? How do we implement these providers well so we get the best performance? And what features are needed by the applications, not just like MPI and Shemin, but also as we move out to cloud? And how do we analyze those features and turn them into something that we can implement inside the API? Like new endpoint types, or do we have the right implementations for like the nano message or 0MQ or Hadoop or Memcached, for example? What features do they want to work well?